right? So right. So I expect that you can, all of you can see my shared screen with this picture about the stellar life cycle, right? So if you can't see, then please let me know. Right. So actually, this picture, before I start about this first section about what triggers the star formation, I want to take some time to explain this particular diagram. And this diagram basically explains that everything that we will be covering about the star formation during next probably within 5 or 6 lecture hours. So within next 2 or 3 days, we will cover all of these things, right? So make sure that you understand it. Understanding this particular diagram will make very easy for you to understand the rest of the sections about the star formation, which I will be teaching in this lecture. Now, right here on the, let me take this, right. So I guess you should be able to see my pointer right here. Right here on the left hand side, you have a molecular cloud, which is what I discussed last time. So that we discussed different properties and the composition of this interstellar matter. And molecular clouds are basically the starting point of a star. And what happens is these molecular clouds, once they satisfy some of the conditions that we will discuss during today's lecture, they will uh, end up creating a protostar, right? So that's what you see here. Protostar is the very initial stage of a star, right? Now, so there are certain conditions that you have to satisfy in order to have a protostar, and we will discuss that particular section today. And then, depending on this initial mass of the protostar, there will the protostar will lead to three different uh, paths as the next step for a star, right? So depending on the initial mass, the protostar can make a very massive star, which is greater than, uh, I guess, 8 times the mass of the sun. This number is not that much important. We will discuss about that. What I want you to know at this point is, after a protostar, you can have a very massive star, or you may have a low mass star, or you may have something called brown dwarfs, right? Brown dwarfs are also we called as failed stars, and we will learn that in today's lecture as well, right? So after you will have a molecular cloud, and then the protostars. From the protostar, you will have either a very massive star, depending on the initial conditions, or you will have a low mass star. Else, you can also have brown dwarfs, right? So brown dwarfs are very low mass stars, and there is a reason that we will have a brown dwarf. And you can see, once you have a brown dwarf, after that this diagram does not continue in that path, right? Basically, we used to call these brown dwarfs as failed stars for a reason. And if you have these low mass stars, they will become a red giant and in their next step. So we will actually talk about each of these steps separately within next few days. And once it becomes a red giant, it will become either a planetary nebula and then a white dwarf, right? And white dwarf can be developed to a black dwarf as well. But we will discuss everything up to this point. Or it can another thing that can happen is this white dwarf can be combined with another star, which will lead to a supernova explosion or a nova, right? So one of these two things can happen by combining with combination of another star. If you have a nearby star, by combining or accreting matter from that particular star, and also by satisfying certain conditions, uh, this can become a supernova or supernova explosion or a nova, right? So for all these things, there are certain conditions that they have to satisfy. So we will talk about those step by step. And for high mass stars, it will become a red supergiant, and after that, uh, after this red supergiant stage, that particular star will go through this type 2 supernova explosion, right? And after this type 2 supernova explosion, there will be a core that will remain after the supernova explosion. All the other materials will be ejected out to the space, but still there will be a core, and depending on the mass, that core will become either a black hole or a neutron star, right? So this is kind of the end of the life of a star, right? And in this last stage right here, I have just shown how you can detect a neutron star. Basically, neutron star is also we called as a pulsar under some conditions. We will talk about those. And black holes normally they emit these X-ray emissions, right? So we will talk about those. And basically, just have this picture in your mind, which will make things very easy for you to understand, right? So that's why I have this picture at the beginning of the lecture, so that you can get an idea what we are going to talk throughout this lecture series. Throughout the next 5 or 6 lectures, right? Now, according to this diagram, so let me talk about the very first phase, which is the first part of the stellar evolution. That is the question that we have: what triggers the star formation? So which means what are the conditions, that initial conditions we should have in order to form a protostar, right? Now this particular image that you see is a nebula which we called as Carina Nebula. This is actually taken from the Hubble Space Telescope, and this is a place where stars are born because it has the right condition for that, right? Now these jets that you see, you can see like jet streams that is coming out, right? So these are actually powered by these newly forming stars inside this nebula, right? Right. So for the question that what triggers star formation, to produce the conditions that is suitable for the formation of stars, interstellar matter are the raw material for the formation of stars. They needs to be compressed to very high density, right? So that is the condition. You know that interstellar matter is available in the space according to our last discussion, and this matter needs to be compressed to very high density in order to form these stars, right? Now to compress this matter into a high density, there are several ways that this uh, can happen, and one of those is that explored through a supernova, which means when you have a supernova explosion, they will send out these shock waves, and these shock waves can cause instabilities and collapse in giant molecular clouds. So these molecular clouds uh, can collapse due to these shock waves generated from supernovas, right? So that is one way of having this. Or the radiation coming from hot young stars also can may help to collapse this interstellar matter to a higher density, right? So that is another way of happening this particular process. And there is another mechanism, that is the collision of these large molecular clouds of interstellar matter, right? So that also can cause instabilities. So that can lead to collapse these molecular clouds into higher densities, right? Now, any of these processes actually can trigger star formation to form new generation of stars. So once again, to trigger the star formation, what should happen is this interstellar matter should be compressed to very high density. And to do that work, which means to compress this interstellar matter into these high densities, the three processes that I have mentioned here may be responsible, right? Or one of those. One is shock waves from the supernova explosion, or the radiation from the hot young stars, or the collisions of these clouds of interstellar matter, right? So any of these things can lead to increase the density of the interstellar matter in certain regions, which will lead to this formation or triggering the star formation, right? Now there are two main forces actually plays the role here when you have this process of formation of stars. That is actually just give me a minute here. Right. So how can a cloud of interstellar matter becomes dense enough to form a star? Now we know that there are mechanisms to increase the density of the interstellar matter, but at the same time, now how can it be dense enough to form a star? Right. So this is actually a competition between two parameters, that is gravity and the pressure. Now all particles in the cloud which is attracted to each other basically from the gravitational force, right? You all of you know about this. Gravitational force is a universal force. Any two objects will be attracted to each other if they have a mass, right? So the same thing applies here. All the particles in this cloud, so they are attracted to each other basically from the gravitational force. So what will happen is because of the gravity, all these particles, so they can be pulled and get closer together. And once they get closer together, the gravity actually increases, right? Because when the distance decreases, the force increases. Because of that, once they uh, uh, become closer a little, then their gravity will further increase. So this may lead to increase the density continuously. So I guess you can understand the physics behind it, right? So this is very simple to understand in this way. Basically, once you have two particles, when they get closer together, they should actually get closer together because of the gravitational force. And the more closer they uh, have, then what will happen is the distance become decreased. Once the distance is decreased, the gravitational force increase, right? Which means when they become closer and closer, the gravitational force become even increases, so that their density will get even more higher, because the density means the number of particles in the unit volume or something like that, right? So which means basically the mass per unit volume. So this mass per unit volume will increase. It will keep increasing, right? So that's what happens due to the gravity. But there is a repulsive force for that, that is pressure, right? Because when we have the motion of these particles within the cloud of interstellar matter, there is an increase in the temperature, which means the pressure will increase, and this pressure will act as a repulsive force. Or pressure will normally act from the central region to the outward direction, which is the opposite direction to the gravity, right? So basically, when more or more particles get condensed, the temperature will keep increasing, which means the pressure will keep increasing. So when increase pressure is increasing, that the force applying from center towards the outer direction will increase, which is exactly the opposite direction to the gravitational force, right? Basically, inside the star, what you have is these two forces. And this is basically a competition between the gravity and the pressure, right? So this is the basic concept uh, behind a creation of a star, and also to the stability of a star, right? So this is why physics plays a major role here. We will not actually go into equations and talk this too much, but we will have actually one equation that I will explain. But this is basically what happens. Right. Now, these instabilities within giant molecular cloud will lead to some regions that are sufficiently cold and dense for gravity to win out over pressure. Now, you know that all the interstellar matter will not become stars. No. So what will happen is once you have this process, there are certain uh, regions that you have these giant molecular clouds. Uh, they are actually cold enough for the gravity to win over pressure, because if it is little bit colder, the pressure will not the force coming due to the pressure will not that much high, right? So what will happen is in that particular situation the gravity wins, right? Because inside is relatively cooler, so that the gravitational force can dominate. And what will happen is, if this is the case, then each of these regions will eventually become a star, right? So this is how stars form or stars begin their life, right? Now, a giant molecular cloud may contain hundreds or thousands of these cold, dense regions. Now, if you take one molecular cloud, it can have large number of regions that are high in density and temperature is relatively low, right? So that can happen as well. Now, initially, these regions have a temperature about 10 Kelvin, so which is very cold. Uh, and basically, if you consider our solar system, this is thousands of times larger than our solar system, right? So these regions. And what will happen is each region, then this is the initial condition, because initially these regions will be very cold and will about have like around 10 Kelvin of temperature. And what will happen is these regions will start gradually shrink in their size because of the gravitational force, right? So the size will become pretty much similar to the size of our solar system at the end. Right? So what will happen is uh, the temperature will also increase at the same time, right? So it is true that these are sufficiently cool to form stars, but regardless of that, when you shrink something, the temperature automatically increases, right? So it will become, or the temperature will be around 10,000 Kelvin at the end, right? Now, each of these new objects that are formed are actually called as protostars, right? So this is the starting point of the formation of stars. Right. Now, let me talk a little bit about the physics behind of this formation of stars. I assume that you probably have done some classical mechanics, and if that is the case, you probably have heard about this theorem, right? Virial theorem, right? So, assuming that you know that Virial theorem, I am going to apply the Virial theorem uh, to show you that there is a specific mass which we called as the Jeans mass. Uh, so that is the mass that a molecular cloud basically should have in order to form a protostar, right? So what actually the virial theorem tells you is, so let me have some these calculations here. guess you can see here that so, so I have put here that if I name K as the total kinetic energy of a molecular cloud and U as the gravitational potential energy, the condition actually to have a collapse in order to form a protostar is that uh, you know that the kinetic energy is mainly due to this internal pressure, right? It is gravity that plays the role in the potential energy or the gravitational potential energy. Now, if we need to have a protostar, what should happen here is actually this second condition, that is 2 times K should be less than the magnitude of the gravitational potential energy. So that is the condition that we should have, right? So I guess all of you can understand the idea behind this, right? Without even having equations. That is actually the potential energy is higher, the gravitation, the kinetic energy should be lower, right? 2 times this condition actually 2 times K less than U, that comes from the basically uh, from this virial theorem, right? Virial theorem basically tells you 2 times K plus U should be equal to 0, right? I don't know whether you have heard about this. 2 times K plus U should be equal to 0, right? That is, so that comes from the virial theorem basically. So if the virial theorem is correct, you can get this second condition right here, which is this one right here. And starting from there, you can get an expression which is the minimum mass in order to form a protostar, right? So this question that I have here is, so if I read through that, assuming a spherical cloud with constant density, gravitational potential energy can be given as, so I am given, this is given for you. U is roughly equal to minus 3 over 5 G mc squared over RC, and mc and RC are the mass and the radius of the cloud, right? Whatever the molecular cloud. And its internal energy is given as K equal 3 over 2 Nk times T. Right? So these are probably the equations that you may have heard, but assuming that they are given for you, where n is the total number of particles given by this equation, and mu is the mean molecular weight. So I assume that all of you can understand these equations, which I do not want to explain it, right? So my aim is to find the minimum mass necessary to initiate the spontaneous collapse of a cloud. So this is what should happen in order to form a protostar, right? This the cloud, molecular cloud should collapse, right? To have that collapse, you need to have a certain condition, right? So that condition basically is derived from this condition right here, from the not Wien's, actually from the virial theorem. So let me change this screen and show you some of this, how to do a calculation for here, which may be probably important for you. Just give me a minute here. Right, so I think that if you do not know the virial theorem is actually this one right here. If you have followed some physics, you should know that. If you don't know about it, just remember the theorem, right? So I'm not going to ask you to prove the theorem or something like that. In astronomy, what we will do is we are going to use the theorem. And this theorem is basically is if kinetic energy is K, 2 times K plus U should be equal to 0. And assuming a spherical cloud with a constant density, the gravitational potential energy U is can be approximated by minus 3 over 5 GMC squared over RC, right? So this is gravitational potential energy, and the kinetic energy K is given to you as 3 over 2 NKT. I think we all know about that, right? 3 over 2 N times KT, and this N can be rewritten by mass of the molecular cloud MC. So I'm not going to define the symbols here because everything is in the presentation, but I will show you how to do this calculation, right? Since you haven't done this before. And then mu times mh, and this mh means the mass of the hydrogen atom, and mu is the mean molecular weight, right? So these are the things that you know. And condition for the collapse is actually, you know, this equation is where you have the molecular cloud in equilibrium situation. But when you have a collapse in the cloud, that is basically the potential 2 times K should be less than the potential energy. So this is the condition for the collapse, right? And you can see that if collapse, the potential energy is the one that should go higher. But according to this virial theorem, there are two terms, so the one should go higher, right? You can understand that. So that means 2 times you can substitute these values for the K. K is K just coming from here, 3 NKT over 2, and then less than U, and this is the mod value of the U, so that is 3 times GMC squared over RC. Now, so there is a standard equation which I would like you to see at the end. Now, this radius that you see here, RC, so that can be replaced by the initial mass density of the cloud, right, which is rho naught, right? So this radius RC, so let me write this. Write this as let the initial the cloud is rho naught, and that can be written as, you know, that rho equal m over v. Okay? So that is rho equal mass is mc, the molecular cloud. Now we assume that this is a spherical cloud, right? So this is actually assuming a spherical cloud. So for the calculation, we assume that our molecular cloud has a spherical shape with a radius of RC. So which means we should have a volume here that should be 4 over 3 5 RC to the power Q. Right? From this, you can get an expression for RC. Just by solving this, that will be 3 times MC divided by 4, 5, and the rho naught comes here. And since you have RC to the power 3 here, this should be 1 over 3, right? So that is RC. Now this can be substituted to this particular equation right here for the RC. Let me see what we get after that. Right, so let me first So you have few equations here. Let me take this equation as 1, and this as 2, this as 3, and take these 3 equations. So I will leave this for you as an exercise, which is not uh, that much hard to do. So that is the minimum mass. So I think I have mentioned this in the first PowerPoint as well. Minimum mass necessary. So maybe this is too small for you. Minimum to initiate the spontaneous collapse, right? So that's how you used to tell this spontaneous collapse. Of the cloud. Let's say, so that particular minimum mass, let's say it is always or should be greater than to a mass called Jeans mass, right? So let me write it here in this way, right? So which means that minimum mass is what we called as a Jeans mass. And if you solve 1, 2, and 3, you will get this answer at the end. So I will leave that for you as an exercise, which is just manipulating those 3 equations to get this answer. This is actually approximately equal. So that will be 5 times KT divided by G mu MH. You will see that all these symbols are actually there so that it's easy for you to get the answer. So this is the answer. So just combine those 3 equations, you will get the answer as this one, right? And this is what we called as Jeans mass. And if this criteria satisfies, then you can have a protostar at the end, right? So that is the condition. And there is something called Jeans length as well, which is the relevant radius value. But for now, just let's do this calculation at least, right? So make sure that you understand this, and this part is for you, right? Just do it yourself and try to get this particular expression, right? In case if any one of you cannot get it, then let me know, right? Otherwise, I just assume that you should be able to get that answer, which is not actually that much harder to do that, right? So let me go back to the presentation again. Right, so I guess you can see my presentation now. And so I have given that information right here, right? You need to show that MJ is this one right here. This condition is known as the Jeans criterion, which I will have explained to you. So just have that in your mind. And I expect that you should be able to do something like this or do something like this or prove something like this by give all this necessary information for you, right? So you don't have to remember like equations that I have written earlier, but I expect that you know you know at least this virial theorem, right? So make sure that you know the virial theorem and you remember it, right? Someone who used to know do astronomy, we expect that they know about the virial theorem. So make sure that you remember it, right? So that's the condition. Now, if that condition is satisfied, you will have a protostar, right? So this is what we talked up to now. And these protostars uh, and its surrounding cloud of interstellar matter undergo continued collapse, with the collapse occurring faster in the inner region. So what will happen is you will have a that particular condition that conditions that we discussed are satisfied, then we will have a protostar, right? And what will happen is this protostar will further collapse, right? And at the end, what will happen is the protostar will become very dense and hot, because you know when something collapses and collapse, the density increases, the pressure at the center will increase, which means the temperature also will increase, right? And what will happen is, as a result of that, the protostar will begin to radiate uh, at the end, and this radiation will come mostly from the infrared wavelength, right? And because of that, the protostars cannot be seen at visible wavelength, right? Now, if some of you try to detect a protostar from your telescope, that will never going to happen, because the protostars do not emit visible light, right? So that is why you cannot see protostars, right? Now, these are things that you have to understand when you are doing astronomy. Right? These features are important for that reason. Now, if you, let's say, if you go somewhere and try to write a proposal for a telescope to detect protostars from optical telescope, I mean, you will not get time, because everybody knows that protostars do not emit visible light, so that you will never be able to see those, right? Right, and then what, as a result of this radiation, actually, what will happen is this radiation will actually hold or uh, prevent acquiring more interstellar matter towards the protostar, right? So because when radiation goes outwards, it will prevent achieving or accreting more matter into the protostar, right? Now, this particular state happens, or when a star is in this particular state, we used to call that particular protostar as a pre-main sequence star, right? So remember, these names are very important for you, because when in the next section, I will use this particular name, okay, starting from the pre-main sequence star. Then you should have an idea what is the meaning of pre-main sequence star. So what it basically means is, initially you had the molecular cloud, and after certain conditions are satisfied, you have a protostar, and the protostar will become incredible dense and hot at a particular time, and it will start radiate, especially in the infrared wavelength. And once it begins this radiation, because of that process, it will prevent protostar from accreting more interstellar matter from the space, right? So when at this particular point, we used to call this particular protostar as a pre-main sequence star, right? And if you remember the last lecture, we draw this HR diagram, and I defined different regions of the HR diagram as far as I remember. And one region is this main sequence, which is this line that goes from, not exactly a line, the region that goes from top left hand corner to lower right hand corner, where 90% of the stars lie, right? So that is the region we call it as the main sequence stars. And this is now pre-main sequence. Now, as the name suggests, these stars are not in the main sequence still. They are pre-main before that, right? And here is just an example of places where you get to have this creation of stars. And this left-hand image is taken from the Hubble Space Telescope. And this is from the Eagle Nebula, right? You will see this word regularly. And the right-hand side is basically the same image, but a close-up view of this region right here. I mean, you can identify it from the two images as well. So that shows a very dense globulus, which is kind of a nursery, or the place that you will have a lot of star formation, right? Right. So let's look at what happens after the pre-main sequence starts. Now, once you have the pre-main sequence stars, they will continue to heat up and gradually shrink in size. So they will heat up, and at the same time they will become bit smaller in size. And what will happen is their temperature will increase, right? Because of the pressure, and will become the temperature up to 10 million Kelvin, right? Now, one thing that you have to remember or note down here is these protostars and the free main sequence stars are created from the interstellar matter or molecular clouds in interstellar matter, which means you should have mostly hydrogen inside that, right? Now, when the temperature is higher, like up to 10 million Kelvin, there is something that happens to hydrogen, right? If you have done some kind of nuclear physics, you should know that there will be a thermonuclear fusion, which as a result of that, this hydrogen will fuse, or hydrogen will become helium, which means there will be a fusion reaction, which makes hydrogen into helium, right? And once this particular process happens, this will release a huge amount of energy, because these are nuclear reactions, right? And this energy use of radiation, and this is the time that we use to mention as the birth of a star, right? It is true that we had molecular clouds, and once they satisfy some conditions, they became a protostar and a free main sequence star. But in general, we used to tell uh, that the star is born when that particular star starts to burn high or fuse hydrogen into helium, right? And as a result of that, the star gradually sheds its surrounding cocoon of interstellar matter and become visible. And these are the stars that you can see in the sky, right? Before that, these protostars you cannot see, for the reason that we discussed in previous slides, right? Now, at this particular point, they will arrive onto the main sequence of that HR diagram. Now remember that it is important that you have this HR diagram in your mind, right? So if you can't remember, please go back to the previous lecture and just have a look at the HR diagram and try to understand different regions. And there was a region called main sequence, which we talked, and this is the time where this pre-main sequence stars will enter into the main sequence. So which is uh, the main reaction there is this thermonuclear fusion that turns hydrogen into helium because this higher temperature, right? So make sure that you clearly understand this process, right? Now this is uh, a chart diagram again, which basically explains to you uh, this main sequence is what you see from this reddish color, the line, that is the main sequence. So if I uh, this line right here is the main sequence, and you can see that there are different tracks that are actually mentioned here, and the star around this lower left hand corner is around zero point 0.5 solar masses. And remember, this symbol I explained to you before is to denote the solar mass, right? Basically, all these things are measured in terms of solar mass, and you can see that depending on the initial mass of these stars, the stars will approach to different regions of the main sequence. And as we discussed in the earlier slide, when the stars begin these fusion reactions, which make hydrogen into helium, they will enter into the main sequence. But where it will be located in the main sequence will depends on its initial mass. For example, If the star is very low in mass, they will go into this lower right hand corner region of the main sequence. You can see that lowest mass is right here, 0.5 solar mass, and 1 solar mass, which is of course our own sun, is around this region. And the 2 solar mass stars are right here, and 3 solar mass stars will go here, 5 solar mass stars will go here, like that. Uh, Depending on their mass, they will be located in certain regions of the main sequence, and the highest mass stars, which is 15 solar mass, will go into locate right here in the top left hand corner, right? And make sure now these things you have to remember and you have to understand, right? So these are very important, right? I expect all of you have a very good idea about this chart diagram by the end of this section, and how different masses are going to different regions. Because the reason is, if you go into study about stars or any astronomy course or research in future, this part is something that you need to know, and it is very important. And you can actually, without having a lot of things remember, just looking at this diagram, you can tell a lot of things. And another thing that you should notice here is the number of years that you see here: 10 to the power 4 years, 10 to the power 5 years, 6 years, 7 years. These are roughly the amount of time a star takes to enter into the main sequence, right? So that is what I have mentioned here. And one thing that you should notice here is these low mass stars, for example, star enter into this main sequence. If it has a 2 solar masses, the time it takes is 10 to the power 7 years, right? So this is like, I guess, 10 billion years, right? Like that. Now, when you go higher up, for example, a star which is 15 solar mass, uh, take only 10 to the power 4, 10,000 years to enter into the main sequence, right? You can see a nice feature here. The more massive stars will go higher up towards the higher uh, left hand corner in the main sequence. At the same time, the time they take to change their process is also smaller for high mass stars, right? So this may be not something that is in your mind. You may think that it is low mass stars may go quicker into their process, but it is not the case. These high mass stars will go into change their process quicker compared to low mass stars. Right? Basically, you will see that when you go through these steps day by day, that these everything, all these processes that we will be discussing will happen very quickly or faster for high mass stars compared to low mass stars, right? So that is because of these reactions will be faster due to these gravitational forces and everything for the high mass stars. We will discuss those things, right? Now you can see that this particular diagram has stars with different masses, right? So next we will discuss about that. Now, amount of mass in collapsing fragment of interstellar matter determines the star's eventual mass, right? So this is something random, that the amount of matter that start to collapse will define the eventual mass of that particular star, right? And also, as I mentioned before, the mass of the fragment also determines how long it takes for the star to form. Now, for example, if you think about a star like Sun, that will take about 50 million years to form, right? And most massive stars, which are the stars that you saw in the top left-hand corner of the main sequence, they will just take like 1 million years to form. And these very small stars, even smaller than the sun, they used to take more than a billion years to form, right? So basically this slide explains what I have discussed in the previous diagram. The more massive stars will be quicker in their evolution, they will form quickly, but for the less massive stars, they will take billions of years to form, right? The mass of the star also determines its main sequence luminosity and the surface temperature. It will have these properties for most of its life. Now, if I go back to this particular slide, what it means is if you have a higher mass, it will go into this top left hand corner, which means according to this axis, the stars in this top region right here will have a higher luminosity, and also if they are towards the left hand side, so they will have the higher temperature. So the stars will, these more massive stars will have higher temperature and higher luminosity, right, on the main sequence compared to these less massive stars. These less massive stars actually will have lower luminosity because they are down here, and because they are in the right hand side, they have a less temperature or smaller temperature as well. Just keep in mind that this temperature scale is increasing towards the left side, right? Not that this is not a usual graph, right? So scale is inverted, right? So that's about that, and let me talk about the brown dwarfs now. So we saw that basically what happened to a star, right? It will become a protostar and then will become a brown dwarf. Sorry, will become a pre-main sequence star, and then depending on their initial mass, the star would become a will enter to the main sequence star and into different locations depending on their initial mass. However, there are certain type of certain set of stars that the interstellar matter mm, so is not enough to turn them into stars, right? So if they need, I mean, these stars actually they will become protostars, but they don't have enough mass to burn hydrogen into helium, right? So this is the problem they have because those particular protostars do not have enough central temperature. According to nuclear physics, you know that to burn hydrogen into helium or for this fusion reaction, you need to have certain temperatures. So that temperature is what we talked before, which is around 10 million kelvins, right? Now, if you do not have this temperature, this reaction cannot happen. Now, there are certain protostars, they don't have enough mass to gravitationally collapse and increase the central temperature to up to this million kelvins so that they can burn hydrogen. Right? If this doesn't happen in a protostar, they will not go into this next step, which is that pre-main sequence and main sequence star, right? They will not go into that particular step. Now, actually, this happens roughly for 8%, uh, roughly for when the protostar has mass less than 8% of the mass of the sun, right? You know the mass of the sun. And if the mass of the protostar is less than 8% of the mass of the sun, they will not have enough temperature at the center, which means the mass is not enough to collapse them so that they will have enough temperature to burn hydrogen into helium or for this fusion reaction, right? Now, if this is the, uh, I mean, because of that, these less mass protostars, we used to call them as failed stars because they cannot proceed from that point towards the next step, right? And these are called as failed stars and then referred as brown dwarfs, right? Now you may see that when you look at these articles in the internet, there are a lot of information about these brown dwarfs, right? Now you should understand what brown dwarf means, right? Brown dwarfs actually give off some light as they gradually cool, but they are much fainter than normal stars, right? Now, if somebody asks you, when you go outside and look at the sky tonight, will you be able to see a brown dwarf? What should be the answer? you cannot see a brown dwarf, right? Because brown dwarfs are so faint, even it's hard to detect from a telescope as well, right? Now, this is why the detection of brown dwarf took a long time until the technology is developed to see or observe these faint objects. Now, the first confirmed detection of the brown dwarf is actually not that much far away. It happened just in 1995, which is 25 years ago, right? Even the technology is developed, you can see that there are a lot of things that we don't know, right? Now, this is actually a brown dwarf, Gliese 229b, uh, which is actually this small object. If you probably see, one is from this Palermo Observatory and the same image from the Hubble Space Telescope in the right hand side. And once again, you can see the difference of the quality of the image, and the Hubble Space image is more clearer. Right. Right. So here are some brown dwarfs just to show you, illustrate, uh, give, give you some illustration about the brown dwarf. The what you see in the from this yellow color in the top left hand corner is our sun, and after that you can see these brown dwarfs, Glee 229A and up to WISE 1828. All of them are brown dwarf, and then there is Jupiter after that, right? And in this lower side, I have given the spectral classes as well. And from the temperature and the spectral classes, you can see that the brown dwarfs are relatively cooler compared to sun, right? So they are very cool stars. They don't emit much light. But then there is a problem here, because most of these brown dwarfs, you can see that they are kind of, if you compare the brown dwarfs with the Jupiter, which is on the right hand corner, is somewhat in the same size, right? And because of that, you need to have a way to distinguish between planets and these brown dwarfs, right? And for that, so we have an issue with low mass brown dwarfs and high mass planets, basically because they looks like the same. So brown dwarfs about the same radius as Jupiter, regardless of their mass. And this covers a range of masses from about 13 to 80 times the mass of the Jupiter. So which means this makes actually it harder to distinguish between those two types of objects, high mass planets and these low mass brown dwarfs. Because of that, the International Astronomical Union now actually considers this deuterium fusion to differentiate between brown dwarfs and planets. So what that means is, if an object has enough mass to fuse deuterium, that is around about 13 Jupiter masses, then we call it as a brown dwarf. But objects with less than 13 Jupiter masses, they can't fuse deuterium, and we used to consider those as planets, right? So that's how you differentiate between brown dwarfs and planets, right? This may be a bit new for you, but just learn it, which is important, right? So that will actually uh, end up this particular section about the triggering star formation. Now we will have some time. Actually, I can start the next section. But before that, if anybody have any questions from this section, you can ask. Right? So until I pull out my next presentation, I will try to cover half of that at least. Right, so seems that you don't have any questions, so let me share the next presentation. Now, remember that it's easy if you like remember this step by step. This is like a life story, right, of someone. So this is like the life story of stars. So we began by discussing different properties of the stars, which will be useful to discuss everything else, and then we discuss about interstellar matter, which are raw materials for stars, and the third step we discuss about the formation or triggering of star formation and what happens in the first few steps, and we discuss up to a point where we have the stars in the main sequence, right? Now let me uh, so I guess you can see my shared presentation right now, which is already shared, and let me start talking about what happened to stars once they enter into their main sequence, right? We talked everything up to main sequence. Now remember that each of these steps you need to have a knowledge about the HR diagram, right? The main sequence is basically coming from the HR diagram, right? So here is a schematic diagram for many number of stars. If you draw a diagram for many number of stars, once again, now if you didn't remember, if you don't remember the HR diagram, this is a good chance to look at it again. The left hand side you have the luminosity in terms of the solar luminosity, which means how many times a star is luminous compared to the sun, and the y-axis, sorry, the x-axis actually the spectral class, and that also gives you an indication about the surface temperature of the stars as well. Now you can see that when you have a large sample of the stars and make this HR diagram, 90% of all these stars fall along this narrow band, which we called as the main sequence, right? So that is actually this region right here. You can see that the 90%, even from just looking at the graph, you can see that most of the stars lie on this line, which is what we called as the main sequence, and the 90% of stars lie in that particular region, right? And minority of stars, so which means some few stars that you can find is upper right. So they basically are actually cool. You can see that their temperature, so that's how you decide it. Just looking at this diagram, the stars in this region are relatively low in temperature, right? In terms of spectral temperatures, they are relatively cool, right? Not in temperatures in our day-to-day life. You can see that they are still around 3000 Kelvin, right? But in spectral relative to the other stars that are in the left-hand corner, these stars are actually relatively cool, and because of that, they have this red color, right? Remember, this temperature and the color is related from the Wien's displacement law, right? Because of that, they seems to be red and bright, right? And they must be giants uh, because they are high in luminosity. Yeah, they are cool, but they are high in luminosity, which means according to Stefan Boltzmann law, the luminosity depends on the surface temperature and the area of the star. So if they are cooler and still they are bright, which means their surface area should be larger, which means they should be very giant stars, right? So that's how you combine physics with these properties, what you see in the HR diagram to explain something, right? So basically these stars that fall in lower, which means this region. So these are what you had as white dwarfs in this very initial block diagram that I showed you. So white dwarfs are basically, uh, they are hot stars. So they are hot, you can see their temperature is higher, but they are not luminous, right? So that the reason should be their surface temperatures again should be very smaller, right? Sorry, you can't tell actually that exactly, but they are dim because their temperature is lower. So let's keep it in that way for now. Right, so let's look at now having this main sequence in your mind. So let's look at how the life on the main sequence for these stars. Now all these stars on the main sequence, so they are somewhat at the similar stage in their lives, right? But they may have different ages. Right? Just remember that difference, right? So when I say that they are at similar stage, what I mean is they are basically burning hydrogen into helium in their course and in their main sequence. But depending on their initial mass, their ages may be different, right? But they are still doing the same thing, right? Now these all main sequence stars, they are burning hydrogen in their cores and converting it to helium at a constant rate. And as we discussed, this is what they have been doing uh, when and what they are doing in the main sequence, right? So this is what we discussed. And hydrogen is the most abundant and slowest burning of the slowest burning of the fuels that a star will burn in its lifetime. So the hydrogen is the mostly available one, as you know, and they are also slowest in burning of the fuels, right? So which means if they are slowest in burning hydrogen, so they will spend most of their lives on the main sequence. The reason is you will see in next few slides that when they stop burning hydrogen into helium, they will leave the main sequence for their next stages, right? But since this process is very slow, star basically spend most of their lifetime on the main sequence, right? Now, this also explains why most of these stars are on the main sequence, because when you take a statistical sample on the sky and make this plot from very large number of stars, you will see that the most of the stars are on the main sequence. This is because if you take a star, it's most of their lifetime will be on the main sequence, right? So statistically, you would expect most of the stars on the main sequence for that reason, right? And main sequence star is very stable because there are pressure and gravity balance throughout the star. So you have these nuclear reactions inside due to the temperature, and this will create pressure, and then there is gravity from the outside. Now, this pressure and gravity is balanced for these stars which are on the main sequence, right? So it is when this balance goes off at some point is the time that they will start to go for these different stages, right? Now, so this particular graph basically table basically shows some properties of the main sequence stars. So what I want to note down here is that these massive stars has shorter lifetime and high luminosity and high temperature, right? So if you look at our sun, which is one solar unit, uh, so it takes around 1 times 10 to the power 8 years for the formation, and it will spend around 9 times 10 to the power 9 years in the main sequence, and then in the giant phase again some amount of years. So what I want to focus on these two columns here, you can see that when the number of solar masses increases, when you go down, the formation years uh, will basically decrease, right? So these are the stars, high mass stars, which are on this top left-hand corner on the main sequence compared to the sun. Sun is kind of at the middle, and the time they spend in the main sequence also is smaller. So when you see that this mass increases and this formation year also decreases, and the time they spend on the main sequence also decreases with the mass. Now you can see that there is a clear relation between the mass of a star and the amount of time that they spend in a particular phase on the main sequence or any other phase in the HR diagram, right? Right. So here is actually life. Uh, Here is kind of you have the spectral type on the first column and the surface temperature on the second column and the mass of those suns and the life on the main mass of that particular star and the life on the main sequence, right? Now, uh, you can see that when you go for spectral classes down, which means that your temperature will come down slow, smaller to smaller numbers, and the mass of the sun, sorry, mass of the star will go down as well, right? Now you can see that the lifetime on main sequence is also will increase when you go down, right? Now this gives you a nice story. You know that this now using this Kepler planet Kepler mission and everything, there is a lot of research that are going for extrasolar planets, which means we now know that there are thousands of other solar systems which is similar to our own solar system. Now there is an attempt going on whether there will be intelligent life, right, on these other planets, other or intelligent life in these planets around other stars, right, which is looks like the sun, right? But from this table, you can see that it will be a pretty big waste of time to search around O and B type stars. And you can see the reason, right? Because the O and B type stars, they don't spend much time in the main on the main sequence, right? 1 million and 10 million, right? Which means they will change their stage pretty quickly. And our own sun is a G type star, right? So this is why it will remain 9 billion years on the main sequence by burning hydrogen into helium, which is the main power source for us. So you will have same conditions in order to have some intelligent life according to the knowledge that we have, right? So which means it is a waste of time actually. If you look at these O and B type of stars, uh, I mean solar systems that have O and B type of stars, right? To look at for this intelligent life, because it's very less probable that you will have life on these stars due to the fact that they spend very small time in main sequence, right? So that's what I have mentioned here. These stars remain stable for such a short time that the development of creatures complicated enough to take astronomy course is very unlikely. You know that. I mean, just I just put it there from a book. Right. So this is again. So you will have the same. I mean the same HR diagram again and again visible in my slides. This is just to emphasize you again and again that this HR diagram, understanding HR diagram is very important, right? Now here I have named some of the popular stars that you know now in the sky. So I have asked you to look at these stars, right? Betelgeuse, Antares, and then probably Aldebaran, I remember. And then you have Vega here, Regulus, and the Sirius here, Altair is here. You can see that they are kind of around top left-hand corner towards the top left hand, right? So which means their lifetime will be shorter. Now Sun is right sitting here, which is kind of G0 type star, and it is right at the middle of the chart diagram, and you can see the reason that and the advantage of having sun right here, because it gives you enough power, and at the same time it will last for a long time on the main sequence by burning hydrogen into helium and giving us uh, energy, right? And these stars that you see now, when you go outside and look at the Betelgeuse, now just keep in mind that it is not on the main sequence, right? It is a red giant star, right? So it has gone out from the main sequence and in the next phase in its lifetime, and you will see that. And the Bernard star is right here, which is a star that has a large proper motion. It is still on the Main sequence, by the way, or close to the main sequence. Right. So I guess I guess I will stop from here since we have just talking for a long time now. Anybody have any questions up to here?
Yeah, sir.
Yes.
I'm having a one question from the
Yes.
first session.
Yes.
Actually, we've studied that interstellar matter are compressed to high density by three methods,
Yes.
and I have a weird thought that in the very first beginning, uh,
Mhm.
is is the collision of clouds only the process which made compression, or is there any other process which involved at the very first beginning?
Uh, okay. So very first beginning, actually the process may be little different because when you talk the stars into like when you just talk only about the stars into much detail, there are different populations of stars. So the very first stars that creates in the universe, which we called as far as I remember, population one stars, right? So their formation mechanism is actually a bit different. So what I am talking here is actually the stars. This is like a life cycle of the star. So when stars die, the matter goes to the interstellar matter and then recreate. But as far as I understand, what you are asking is when the very first star formed in the universe is this is it sorry has it has the same whether it has the same process, and the answer is actually no, because these very first stars have a different mechanism. So they are called population one star, right? One stars. And we have these different stages of the stars. So I wouldn't go like into too much details into those steps in this particular lecture, but yes, so there can be a different mechanism for those stars, right? I would give some few details since you asked about that. I will next lecture probably I will add few details about those population one stars. Right. So
Okay, sir. Thank you.
right. So if anybody have any questions, you can ask. Right. So if not, so let me stop from here. But before I leave, there are few notices for you. Now I have to finish these lectures actually a bit quicker. Because of that, I expect to have lectures in next. So you will not have lectures tomorrow since it is a Sunday. I don't want to continue the lectures for each and every day, but you will have a lecture on Monday evening and expect a lecture on Tuesday morning as well. So right, there will be two lectures on those 2 days, right? Each will be 1.5 hours mostly, and the morning hours will be uh, it will be around 8 a.m. on Tuesday, right? So I hope all of you are free of that time. So if you are not free, then let me know. Then I will have another lecture tomorrow as well, right? If you cannot do it on Tuesday, right? And then we most probably will have another one on Thursday as well. So these final lectures I probably need to within 1 or 2 weeks I have to finish all these things, right? So I will post a notice in your